Hello, hello, hello. Okay, I think we're on. It's the post-lunch slot, so I imagine people will turn up a minute or two late. So it does appear that Docker is still popular. Yep, still quite a few people turning up for Docker talks. Before we dive into what my talk's going to be about, which is running JVMs inside Docker, I'm going to ask you to do something really crazy, really weird. I'm not going to ask you to do star jumps, etc., because you've just had lunch. I'm going to ask you to come and work with me in the UK. And you might think we don't want you to come and work in the UK, but I think we still do. So if you're interested in any of the stuff I'm going to talk about today, go and see the Sky stall. I'm an independent, but I work mainly for Sky at the moment. What I do there is I build a PaaS, like a platform as a service, for lots and lots of other developers to deploy their applications to. Just before I came out here, I actually just checked how many JVMs are running in there. It's not too big, but it is into the hundreds now. So we've got all of our applications for various environments, like integration tests. We've got non-JVM applications as well. We've got mocks. We've got demo applications. And the developers get very grumpy if this doesn't work all the time. And that's kind of what I do at the moment. So rather than write Java, I work with Ansible and write Golang and contribute to Kubernetes and all sorts. So what I want to talk about today is spend a very short amount of time talking about the motivation for actually putting your JVM inside a Linux container. I actually don't care whether you're using Docker, whether you're using, cgroups namespaces directly, whether you're using Rocket. It's just that most people, when they're using Linux containers these days, are using Docker. The reason I want to spend a few minutes talking about the motivation is I can sometimes be a little bit negative about Docker. I can sometimes maybe suggest that people do not do it. So I really want to say that I do think it's a good idea if you have a certain set of requirements. And if you don't have those requirements, I would suggest not putting your JVMs inside Docker. Once I've done the semi-Linux container sales pitch, I want to talk actually how they work under the covers. So we're going to be talking about a couple of Linux features. We're going to be talking about, very briefly, about namespaces, but primarily about control groups. Now, control groups are an interesting topic, and it's the way in which Linux allows you to separate resources and give, say, a certain number of CPU cycles or a certain amount of RAM to these processes, etc. And it's what Docker uses under the covers. And it's actually that makes running a JVM inside a Docker container interesting and sometimes challenging. So all the examples I show you are on GitHub. You can go and play with them. This is a project which I'll share the link for at the end. And it essentially contains a Gradle project that will build you 3 Docker images, the ones we're going to use today. And then we're going to put some load on them. I'm just going to show you screenshots rather than do it live and see how it behaves differently to, say, a JVM just running on a regular server. I'm not going to care about Docker Compose today, but I have checked in a bunch of Docker Compose files, and if you don't know what Docker Compose is, it doesn't matter. It's just a way of kicking off some Docker containers with some pre-canned configuration. And that means that when we see how certain containers work when they've got so much memory, so many CPU shares, you don't need to remember that. You can just do Docker Compose up, and I've got a bunch of files which look like this. The scenario that I'm going to play with is one similar to what I've got at my current work. We've got a bunch of Java applications. Some of them are built with Ratpack. Some of them are built with DropWizard. And all of them, because we distribute our services far too much, make lots of calls out to other services. So I thought a realistic example for me would be to have one JVM running inside a container running Ratpack. Now, Ratpack is a non-blocking framework. It doesn't use a thread per request like, say, you're used to with Tomcat or Jetty or using Spring Boot, for instance. And what they're both going to do exactly the same thing. All they do is take a web request in, make a call out to a wiremock. Wiremock is just a HTTP stubbing service. The important thing to note is it is real TCP. It's a real network call which takes time, which does matter. All of the examples while I was preparing this talk are on my desktop. Now, you might think, I'm running inside a Docker container. Why do I care about what system it's running on? And you'll quickly find as you run more and more JVMs inside Docker containers, you really do care about what system it's running on. So the fact that I was running these examples on my machine, which has 12 cores and 64 gigs of RAM, will become very relevant. And it's very easy to break your production environment if you change the underlying host. So we see some load going through these containers. I'm just going to hit them with Apache Benchmark, which is it's a noddy load generation tool for HTTP. Not important. So before we jump into seeing real examples and real containers, I wanted to talk a bit about the motivation for running JVMs inside Linux containers. So think about how you deploy your application. Are you using something like Tomcat or Jetty as an actual application container? Like, are you deploying WAR files to it? Or have you got something like JBoss or WebLogic or WebSphere or some kind of app server? Now, sometimes using those these days is frowned upon, but especially at the conferences. But they did give you this awesome abstraction between the underlying hardware and your application. You built that WAR file, and it sometimes works the same inside the production Tomcat than it does your local one. Sometimes it doesn't. But more recently, I've moved to building a lot of executable jars. So this is where we use things like Spring Boot or Drop Wizard, and we just build it from scratch. We actually have a main method. Who wrote a main method recently, right? And then you actually just start up a Jetty, and then you add some handlers, and then maybe you add Jersey when you want some kind of request mapping. And the problem with moving to this, and this is what I've done a lot over the last few years, benefits are the only thing an executable jar has as a dependency, assuming you've built all of its like jar dependencies inside it, is a JRE. Now that's really good. So, we don't suddenly have to worry about the version of Tomcat. We just have to worry about the version of Java. Now, one issue with that though is that when we come to want to deploy multiple applications on the same host, and there are some really good reasons for doing that. Often we're building executable jars into things like RPMs or, say, deb packages, and they're getting deployed to our servers. And then we go from deploying many applications on the same host to just deploying one. Now, this can become rather expensive. Who here, not that I can see you, runs an AWS? It is getting extremely popular, all right? And AWS have this really cool tool. This is from quite an old account. I don't use this one anymore. It's a thing called Trusted Advisor. It's quite a funny tool because it tells you how to give Amazon less money, and it's produced by Amazon, which I find kind of weird, but they do give us this tool. They allow us to say, hey, you're wasting $106,000 a month because you've got underutilized instances. And this was an environment where we were deploying, executable jars, and it was the only thing running on that host. So there are some motivations for wanting to run many applications, many JVMs. And we even tried to, in this account, we did try and shut things down at night. We tried to use the smaller instances. But basically, I could have bought myself a Porsche every single month if I'd actually just had high utilization inside this Amazon account. I like Porsches, so. But running multiple JVMs on the machine can be quite challenging. So I used to do a lot of work with Apache Cassandra, which is a database written in Java. And then I used to do a lot of work with Apache Spark. Now, Apache Spark is written in Scala, but it's a JVM application. And you often wanted to run them on the same host. And what you typically have is then very resource-hungry Java applications all trying to use all of the memory, all of the CPU cycles, etc., and it can become troublesome. So if we're going to think about using Linux containers, we want it to help with that problem. And the reason it is such a problem is the same reason that sometimes running a JVM is actually quite easy. Now, some people laugh at me when I say this, but a lot of JVMs run without too many configuration parameters. Okay, maybe they have a few, maybe they have some for garbage collection, young gen sizes, picking, but in general, it's probably under 10. And the reason for that is that JVM doesn't hard code a lot of its values. Right? It doesn't hard code the amount of heap it should use. It tries to work out what is the best amount of heap to use given how much RAM is on that host. But that completely falls down as soon as we run multiple JVMs on the same host. So a lot of the problems which you face running Java inside or JVMs inside Docker, you'll experience very similar problems if you just run lots and lots of JVMs on the same host. So hopefully that gives you an idea of why I think we should use containers, right? I haven't told you how yet, but I have said that they're hopefully going to help us, give us the ability to run lots and lots of JVMs on the same host and buy me a Porsche every month. But if we're going to use them effectively, then we need to understand how they work. Now, there are two main areas that we need to look at to do this. So one is Linux namespaces, and the other are Linux control groups. So we're not going to spend much time on namespaces because I don't think there's much JVM specific there. But just know that you have a namespace that isolates things inside Linux. So you can have a process namespace, so you don't get to see the other processes on a box, inside a container, sorry. So if you jump onto if you run like bash inside a Docker container and you run PS, then you don't get to see all the processes, which is good. Probably more importantly, there's say a network namespace, so we don't all try and open port 8080. If you've had a shared, say, Jenkins CI server before you had, spinning up Docker slaves and things for it, and you tried to open a port when your test was running and you didn't try and find a free one, you probably experienced the problem that this solves. But what we really want to talk about today, the things where I think you need the practical skills to run our Java applications inside Docker, is to understand exactly how cgroups work. It's yet another thing you have to learn. You have to understand how the JVM works, you have to understand how Linux works, and now there's an extra bit we have to learn. So that's why I say only do it if you actually need to run lots of applications on the same host. So my way of showing you control groups, I'm not going to try and explain them, I'd be terrible at that, is just to show you examples of containers running and when control groups get involved. They're essentially the Linux feature which allows you to divvy up resources, say CPU and RAM, and say that, hey, this process, this Java application can have this much, this Java application can have this much. Some of the tools we're going to use to inspect our running containers, our running Java applications, I've listed a few of them up here. Some of them I imagine you've used for years, like PS and top. An interesting note is a lot of tools are inherently namespace aware, but generally are not cgroup aware. So if you jump onto a container and run top, it can't see the other processes, but it's very likely to be able to see all of the RAM on that machine, which becomes interesting. We're also going to look at tools which are nothing to do really with Docker. We're going to look at things which are to do with control groups. It just happens that Docker creates control groups for you. So we can use these tools to diagnose problems with our Java applications running inside Docker. So a couple of those are a few from systemd called cgroup ls and cgroup top. So we can actually see the resource usage of a particular container. Now that could be one Java process, or you could have started it, say, with a shell script and it would be both. To give you some context about what these actual specific containers I'm going to show you do, they all inherit from this very simple base image. I've inherited from the Fusion base image. Now, if you're using Docker and you haven't read the articles about the Fusion base image and about the PID1 problem, about zombie processes, I suggest you just have a Google and go and have a read about it. Not to say you have to use it, but it'll definitely discourage you from running Java as the PID1 inside your container. All I really do is download a slightly old version of Java. Sorry, that's 66, we're up to 92, I think now. I copy in my favorite start JavaScript, which is going to include just some of the default options that I always want to run when I'm running a JVM inside a container. Then for each of the actual applications, the drop wizard, the rat pack, the YMOC, I have another image which basically inherits from this base image, so it has Java, and then it uses the start JavaScript to kick off its process. Now the Gradle project, if you want to play with this yourself, will build the fat executable jar. So you'll just end up with 3 local images if you run Gradle build on that project. So let's give ourselves like an actual view of what a namespace really is. So I'm sure you're aware that when you're running Docker and you've got a running container, you can execute a command, an additional command inside that container. And one of the most common things to do is to execute bash or shell or some process like bash. And that makes you feel like this is a virtual machine. It makes you feel like you're inside that container. And if you were to do that, and you run a tool like PS, which I've done at the top there, then we only get to see a small number of processes. The host I'm running on here has lots and lots of processes running, whereas we can only see 12 of them. What we can see hidden away there is our Java process is there. Third from the bottom, it's Java, native memory, etc. Now, you might think you have to do this quite a lot. And I'm going to try and encourage you not to do this very often, because control groups are about limiting the amount of resources which a set of processes use. Like, the Java process doesn't get the entire, say, 300 megabytes of RAM to itself. It's sharing it with some of the other ones that are started and my bash process. So if I were to run something else from this bash command, and I were to say sort a log file, grep a log file, that memory usage would be accounted to my Docker container, and then Linux could kill my application. So if you've got a problem with your Java application, you run bash, you jump into the container, you run something else, quite frequently that will kill your Java application. So we try not to do this too often. Suddenly where the kind of analogy of containers are a bit like VMs is suddenly going to die away, because we can find the same processes on the host operating system. They're just regular processes. There's nothing special about them apart from they're running in this special-ish control group. So this Java process we've got when we jumped into the container is this same Java process I've got at the bottom here. So this one here of 29895, Java minus, you can see the native memory tracking option. So once we know the, I'm going to call it the host process ID, then we can use all the tools, all of the methods that you're used to when dealing with Java applications. We can actually just do that on the host. We don't need to run bash inside the container most of the time. So once we've done that, and you just imagine I'm hitting that container with some load, we can use regular tools that we're used to using, like htop. And right at the top there is the Java processes highlighted in light blue, 29895. That's a Java process running inside a Docker container, and I'm running htop regularly from the host, not inside it. So I suggest you start doing that type of thing so you don't inadvertently kill your container. Of course, we could just run top if we don't like colors, and it's right at the top again, 29895. It's using 183% CPU because I'm hitting it with Apache Benchmark at the moment. Actually, you can see AB is about 6 or 7 processes down. Now, that method works, like doing some PSs or some greps, if you have a small number of containers running on the same host. What happens if you've got 100 or 50 or a large number, actually any more than about 3? That is when I would start to use things like cgroup top and cgroup ls. So I'm sure you've done Docker PS, and if you haven't, that lists the currently running containers. And you get this ID, this UUID that is assigned to that container. Well, fortunately, Docker uses that UUID as the name of the cgroup that it puts your process in. So even though cgroup ls has nothing to do with Docker, we can use it to actually see which processes are inside our Docker container. So here I've done cgroup ls. We can see the parent cgroup is Docker, and then under that, now Docker PS truncates the UUID. So we can see it's much longer, but it is the same as the one from Docker PS. Now, you might be jumping onto a host which doesn't have cgroup ls installed. All right, so install it. No, if you can't install it, all the information that comes from this tool is stored on the file system. Everything about cgroups is there. So if we actually look into sys fs cgroup, or certainly on Red Hat distros, everything is there. We can see, look, for memory, Docker, and then the folder name matches the cgroup name, which matches the Docker ID. And if we actually went into that folder, we would see the processes. So even without the tools installed, we can actually go and work out, which actual normal processes are inside our container. This led me to be able to solve a problem which I probably would have taken much longer if I didn't, because a lot of the time we pass parameters to Docker, like we want to set the amount of memory, the amount of CPU cycles it's allowed, and we get really cryptic error messages like this. It says like system error, unable to write to file system. Have I got a problem with my disk? I don't know. But in this example, we know that that's just a file system used to store all the information about cgroups. So it's actually Linux just telling me that I've made a really stupid decision about whatever I've set at the bottom there, the CFS quota US. All right? So knowing that that's how cgroups work under the covers and where it is means like, all right, I must be setting something stupid to Docker. If you want to know lots more about this, I definitely suggest you go and have a read of the Red Hat documentation. It is absolutely fantastic explaining exactly how cgroups work. Way better than the kernel docs. Like, it is a really good resource. And you can go in, and the implications for how, say, the CPU throttling works is really important for your Java application. We're going to see some examples of that. Before we have a look at CPU, though, let's think about memory. Java applications like memory, don't they? So we want to see exactly how cgroups memory allocation works. What does it do when your Java process uses more memory than you've assigned to that container? And maybe you've used Docker on your laptop, which I do a lot for like just kicking off applications. Maybe you've never set a memory limit. But the whole reason that we want to use Linux containers in production rather than on our laptop is so that if we've got two separate Java applications and one of them goes rogue, we don't want it to be able to take out the other Java applications. Which, if we don't set any limits for things like memory and CPU on our Docker containers, it will just eat it up, and everything will end up dying. So if we want to do this in Docker, we just pass an extra option into Docker run. This is virtually all the names of the CLI parameters like memory for Docker are the same inside cgroups if you just go and read that Red Hat documentation. Now, one interesting thing to note, and I've touched on this a little bit, that if we were to just jump into that container with bash, that thing I told you not to do, but I've just done, and then we run free. Free tells you the amount of free memory on a host, and -m at the top there means that essentially I want it in megabytes. Now, even though I'm kind of like, I'm in the container, I'm in the matrix, I still get to see all 64 gigabytes of RAM. Now, that's where that abstract whole analogy, it's a bit like a VM, just like falls over. We won't be able to use that anymore. And this is the main problem as well of the CPU that causes JVMs and containers not to run very well by default. So one of the funky options inside my start JavaScript, which I'll show you here, is that it does set the min and the max heap to 256 megabytes. So rather than using adaptive heap sizing in the JVM, I'm just like, allocate the heap up front. Now you might think that is a terrible idea, and we should leave the JVM to do what it wants. But my whole motivation behind normally setting it to the same when they're running inside a container is I want to know whether that container has the potential to die as soon as possible. Now, what do you think will happen if when we run Docker run and we've set the memory, we've set the amount of heap, not the whole JVM memory, just the heap, to allocate 256 megabytes up front? Who wants to shout out? What do you think will happen? Bad, don't say bad shit. Yeah, it will get killed. So this is the whole point of cgroups. It's basically, I've said I want to give these processes this amount of memory. If they try and use more, I want someone to come along with a sword and chop it down. Now, sometimes Docker will tell you when this has happened. Sometimes it won't. It parses syslogs and things, and sometimes works and sometimes doesn't. But dmessage, which is a really cool tool in Linux just to show you the most recent logs out of the kernel, will always tell you. So if any of my JVMs always vanish, before I even think about doing anything else, is I just run dmessage. And it tells you explicitly. The red doesn't show up so well on this screen, but it basically says, killed process Java because it used too much memory, more memory than is in the cgroup. And this isn't Docker doing this. This is the control group doing it, which Docker set up for you because we passed in the amount of memory. So we obviously need to give this Java application, our drop wizard application, a bit more memory. So what do we think would happen? We're going to do a vote on this. I can just about see you. Who thinks if we set it to 300 megabytes that it will survive? Who thinks it will survive? No one. Who thinks it will die? Okay. And about a third don't care. That's fine. So I actually, when I first did this, when I was tinkering around, and it will depend a bit on how your Linux distro is set up, I didn't know, but it did survive. And it actually shocked me, because I know the JVM uses a lot of memory that's not actually in the heap, and we're going to go through each of those areas later. There's a slight caveat, though. It was really slow. So I hit the same drop wizard application with Apache Benchmark, and the throughput had gone down considerably, like less than half. Now, I want to diagnose what's gone on. What do we think? Well, I run Docker PS. Let's make sure it's really running. And it was. It's there. I'd obviously been away for a while because I'm not sure what I was doing in those 5 minutes before I ran Docker PS. But what I then would do is have a look at cgroup top. So cgroup top is a bit like top, but rather than per process, it's going to give us per container, or per cgroup. So if you've got many processes inside your same Docker container, it's actually the aggregated, the total CPU usage and memory usage. And again, the same ID that we get from Docker PS is going to be inside cgroup top. And we can see it's using 298.9 megabytes of memory, which is, it sounds about right to me, because if you remember, we gave it 300 megabytes of memory. So why is it so slow? So the next tool, which I've only just started using recently in the last year, there's a great blog by a guy called Al Toby about tuning Apache Cassandra, and that's a JVM application. He swears by this, so I now swear by it. But essentially, it is all of the other Linux tools you normally use, all kind of like munged into one and made extremely colorful. So the options I've got here have things like load average. Now, I started this off, and this is giving us a metric every 10 seconds. So when I kicked it off, right at the top left there, we can see the load average is less than 1, virtually nothing happening on this machine. And it gets bigger and bigger and bigger as I'm running Apache Benchmark and I'm hitting my, my Drop Wizard application running inside that container. It shows us loads of information. You get used to watching this, I think. And it shows us the amount of free memory on a machine. So slightly further along, we can see we're using 10 gigabytes of memory, and we've got 44.6-ish gigabytes of free. So there's loads of free memory. It will show us things like context switches. So that's where things have to come on and off the CPU. We can see that at the start, it was in red, and it's in the single-digit thousands. It's 7,486. So that's CSV under system. And then it went massive. It got really, really big because we were running a Drop Wizard application, which is a thread per request. And it got into the hundreds of thousands of context switches while we were doing that. But the really scary column in here, now, I've ran this a lot on Cassandra clusters, so this is the scariest thing you can see on this, is that it was paging. All right, it says swapping sometimes is often used. And that's actually meaning that some of the memory we're using is not in the resident, it's not in RAM, it's actually on the disk. So we're actually using memory that's on the disk rather than in RAM, which seems completely baffling given that we have 44 gigabytes of free RAM. Now, if I'd looked closer inside our cgroup top, it would have also told me about this, because our container is using 356% CPU. It's using nearly 300 megabytes of RAM, which is what we allowed it to use, but it's also doing disk I/O. And this is confusing because this application is just making a call out over the network. It's not actually doing I/O, like disk I/O. If we looked inside htop, on this system, the swap column is always 0, but it managed to jump up to nearly 200 megabytes. So it's almost as if that JVM process is using its 300 inside memory and using an additional nearly 200 megabytes. Now, normally, every machine I have in production has swap off. We'd rather things die than run slowly because we have multiple instances of every single one of our applications. So it's really bad for a slow one to be hanging around. I'd rather it get killed, maybe alerted about it, and we work out why it's been killed and say change the configuration. Just in case your container, your Java application ends up inside a host which doesn't have swap disabled, you can disable it essentially with Docker by setting memory swap to the same as memory. Now, that's a bit confusing at first because I just thought that would be the amount of swap it's allowed to use, but actually it's the total. So we're actually saying you have 300 megabytes of RAM and you have 300 megabytes of RAM and swap. So that's why this essentially disables swap. So what do we think happens to our poor Drop Wizard application when we set this additional parameter? Any thoughts? Is it going to survive? Is it going to run fast, run slow? No, this one goes back to dying. Because we're allocating the 256 of heap up front. It's using other memory for other things. And then it's using more memory than it's allowed to in that control group. We get the nice memory message. We even get a list of the processes running inside that container and how much each of them are using. So that can be really useful debug information inside dmessage. So of course, that means that we need to understand the other memory areas inside our JVM. Now, you may have done this before on other Java applications because, maybe you're trying to tune things and see if there's a native memory leak in one of your libraries or something. But in general, if you're running one JVM on side one host and it's got plenty of RAM, you might not worry about this and you might just rely on ergonomics. But essentially, we need to, if we want to actually get benefits from Docker, from Linux containers, we need to try and make our JVM as small as possible so we can run as many of them on the same host as possible so I can have a nicer car. So we need to understand the heap usage. That is by far the easiest. We're used to looking at heap. This is really normal. We also need to understand the cost of the number of threads we're creating inside our application. That is a big memory user, especially on 64-bit systems with large stacks. And there are other things like the metaspace and code cache and garbage collection uses some memory. If we're using these fancy frameworks that use, say, SumMisc and Safe to allocate memory, or they use direct byte buffers, this memory is not on the heap and is not accounted for and is not limited by the size we set for our heap. So the Ratpack application, which uses Netty under the covers, which uses a lot of direct memory, it uses a lot more off-heap memory than the Drop Wizard application, which doesn't use a huge amount. Now, to have a look at what's going on, you kind of saw this a bit yesterday, if you were in my talk yesterday, but we're going to use native memory tracking. I don't think I'd ever run a Java application inside a container or in general without this option set, because I want to be able to see this on a regular basis. It allows you to see what's using what memory for your Java application. Now, I'm guessing a lot of people here have used JCommand. If not, get used to it, because everything seems to be moving into JCommand. Now, I've done something silly here. I'm running bash inside my container, which I probably shouldn't do. But most of the hosts which I run Docker on don't actually have Java installed. They're just running Docker. So I don't actually have jcommand installed locally. So I have jumped into my container here. And if you run jcommand without any parameters, it lists the JVMs that it's running. And it only gets to see the ones running inside this container by default. And we've got jcommand itself, process 166, as well as having our Drop Wizard application, which is like process 25. Now remember that we're inside a process namespace here. There'll be a different process identifier, running on, when you look at it on the host. Now, if you run jcommand, then the process ID, and then you run help, it helps you. It tells you all of the things that you can do with this JVM with jcommand. And the one we're interested in today, we're going to use a couple, but right now we're going to use vm.native memory. Now that doesn't just show you native memory. It tracks memory in the native code, I guess, but yeah. It'll actually give us a breakdown of every memory area the JVM uses. If you've got something like mission control attached to a JVM, you can also execute this from there. And if we look, this was a Drop Wizard application. We'd hit it with, I think, 12 concurrent requests. It was using, at the top there is the heap. So we can see that it's using, 260 odd megabytes of memory for the heap, which is exactly what we'd expect because we pre-allocated the heap up front. We set the minimum to the maximum. Now, there are some other ones in there. Classes use 27 megabytes. Code uses 19 megabytes. But the biggest by far, apart from our heap in this example, is the threads. Now, this is the actual thread stacks. So to achieve this load, we've required 102 total threads inside the JVM, which does seem quite a lot. And that means it's using over 100 megabytes of memory. Now, another thing we can do with jcommand is get a list of all the threads. We can get a thread dump. Now, you might have signal JVMs for that, signal -3. But essentially, the benefit of using jcommand for this is you know where the output's going to go. Like, there are many JVM processes that I don't know where standard out's going for at the moment. Whereas this, it comes to the standard out of jcommand, which is useful. So our Drop Wizard application, for some context, it has an embedded Jetty, which is very similar to Tomcat if, say, you're using Spring Boot, or you could be using Jetty with Spring Boot. How many threads do you think it needs to service its requests? Now, this is all default options. I haven't tried to tune anything here. And I could try and work this out because Drop Wizard are very kind. They actually name their threads. I wish everyone named their threads. So we can run jcommand for this process, and we can grep for DW, and then we can count it. And it will actually tell us how many threads have got DW in the name. So to service our 12 concurrent requests, we somehow, for some reason, had 65 drop wizard threads. No? Now, drop wizard isn't just made up of its request threads, the ones that are given to you as your application. You also get threads which are dealing with network stuff. So we've got these things called selectors that actually are used to read data off the network and then are passed to your application. Now, these are called selectors, and there are 24 of them. Now, that is a suspicious number. If you think back to about the third slide or so, I told you I was running this on a machine with 12 cores. And unsurprisingly, if you're only running one JVM inside or on a host, or perhaps you're running one JVM inside one Docker container on one host, then picking the number of selectors and acceptors and things based off the number of cores is a really good idea. If we've got 30 JVMs running on the host, it is a terrible idea. Now, we're not going to stop there. We've also got acceptors. These are the things, this is a thread pool that is actually going to accept new connections. And that one is 12. Again, very suspicious. And if we go and look at, say, the Jetty configuration, oh no, I've got one silly example first. Now, you might think, do I care? Maybe it'll just perform a bit worse. But this actually led to one of the funniest outages that I've seen. So we had this Docker image, and we believed the hype. You know, you run your Docker image, it's immutable, it runs the same on your laptop as it does in production. We had an image which hadn't changed for a long time, and then one day, and I recreated this on my host, none of our applications started. And it was with this cool exception, Java illegal state exception. Insufficient threads, max 5 is less than acceptors plus selectors. Now you might think, what's going on there? And it's actually Jetty being really kind to you. So this was for a really low throughput application. We only wanted about 5 request threads, and we'd set it that way to stop it creating too many on startup. However, we changed the Amazon VMs that were running under the covers, and suddenly they had more cores. So that meant that the number of selectors and acceptors changed. So the same container, sorry, not the same container, the same image, so what should have been virtually the same container, wouldn't start because the acceptors and selectors were set differently because it was based on the cores. Not good. So one thing you're going to need to do when running your JVMs, your Java applications inside Docker, is find every single thing which has made a decision based off the number of cores, because Docker containers do get to see all of the cores. If you go to runtime, get system information, etc., inside Java, you will see everything. You'll see all the memory and all of the threads. That doesn't necessarily solve our problem. Like, even if we did actually want a high throughput application which is making these blocking calls out, so drop wizard for instance, if we can drop the request threads and the selectors and the set acceptors all down to a very low number. But if we want to achieve actually like 1,000 concurrent requests, we do need 1,000 request threads. We do need then a larger number of acceptors and selectors, which means that we do need a large amount of memory for that container, and we won't be able to fit lots of them on the same host. So one thing that we've done is move away from Java, the JVM, and just use Node.js. Not really. So there are lots of like similarly threaded applications which work on the JVM. So you've got things based on Accra. I've done a lot of work with Accra. It's a fantastic framework, but it does take over your application. Similar with Ratpack. Or even if you want to stick with Spring Boot or Drop Wizard, they now both have async interfaces where we don't need to block a thread all of the time. But anyway, even if you make the decision to actually move away from a framework which blocks a thread per request and then uses, say, a megabyte of memory, and then your container has to have lots of memory, you don't suddenly get everything for free. So if we do this similar kind of thing for the Ratpack application. Now Ratpack, it works differently. It only needs a thread while you're doing something, not while you're, say, waiting for a HTTP request to come back. So you give that thread back to Ratpack, and then it services another request. So it quite sensibly bases the number of threads off the number of cores. Now, this is not as bad as when we had thousands in, say, in a drop wizard application. We're not going to use that many resources. But we should still configure this and set this down. And we normally just default it to one per core. And you also need to find all of the well-hidden JVM options that affect other things. So garbage collection. The concurrent garbage collectors, G1, CMS, they base the number of concurrent collector threads, GC threads, off the number of cores. So if we do this, we have 15. Now there are 12 of some and a few of others. Compiler threads, things which take your bytecode and turn it into native code, when you get hot code. Then that is also based off the number of cores. Now this grows much slower, so you don't end up with like a 1-for-1 or 2 of those per core. It grows very slowly. If you've used parallel streams, you've jumped to Java 8, and you do any form of parallel streaming, or you do some any of the async methods on, say, completable features without passing in an executor. Well, this also uses the default fork join pool, and that bases its threads off the number of cores. I'm starting to sound like a broken record. If you look at your database drivers, your HTTP clients, any frameworks you've got in there, chances are the thread pools are either really dumb, they're hard-coded to some value, which isn't good anyway, or it is based off the number of cores. So I've talked a lot about cores and about threads, but primarily for memory usage. But if we want to divvy up the memory amongst all of our Java applications running inside containers, we also need to separate the CPUs out so that one process can't go crazy being a large garbage collector with loads of work going on and use up all of the CPU cycles. So the other thing which Docker exposes is the CPU limiting ability of control groups. Now, this is a lesson. This took me a while to get my head around. It can result in some really weird behavior of your applications when running inside a cgroup. So the whole premise of them is to be able to, so if we run our drop wizard application, we've limited the memory perhaps, but we haven't limited the CPU resources, and we just hit it with 12 concurrent, a bunch of concurrent requests. We can use cgroup top, and it will use hundreds, it'll use up to 7 cores by the looks of it for this run. So 700% of CPU. You can see that in top as well. Now, what we need to do, and that would be fine if we're only running one container, in which case, why are you using containers? But if we want to run many of them, we need to divvy out the CPU resources. And there are a few ways of doing that. So you can use CPU sets. This is where you actually explicitly name CPUs that your application, your Java application, can run on. So there's a Docker compose file which sticks the wiremock, the container which is being called out to, onto process 8, 9, 10, 11. Whereas the Ratpack app has to stay on, core 2, and the Drop Wizard app has to stay on core 1. Now, if we were to rerun the same test, we were to boot up the Drop Wizard application and hammer it with some load, rather than the 700% of CPU, we get pinned. We've got exactly 100%, which is kind of maybe that's what you want. But this system's still pretty idle. Why aren't we using the other CPU? Perhaps you only want to limit things when there is actually contention. And for that, we've got these things called CPU shares. So rather than naming particular cores, which can be quite flaky, especially if you're moving applications around to different hosts, you can actually say, I want this Java application to have this proportion of CPU and this one to have that. And those are a relative weight. So what I'm actually saying here by having 4096 as the wiremock configuration is that it gets 4 times the amount of CPU as the Ratpack application and the Drop Wizard. The reason I've done basically 1024 normalized by that is that's the default amount that your container gets if you don't set anything. Now, if we were to do the same thing, we were to load, put a bunch of load on our Drop Wizard application, you just have to trust me here that the Drop Wizard application is the third one down. It's using 676% CPU. So even though we've set its shares to 1024, because it's the only thing that requires CPU usage on that box, it's allowed to use the unused shares from all of the other containers. Now, this might be exactly what you want. We run our Jenkins slaves in this manner. All right? It basically means that if you're working hard during the middle of the day and the rest of your colleagues are, then essentially you get an equal amount of CPU each. Seems fair. Whereas if you stay late because you're really dedicated and you just kick off a job in one of our Jenkins slaves, you'll get the entirety of the CPU. Now, the problem with CPU shares, or at least in my experience, is it's very hard to do capacity planning for your application. So you might think, yeah, I want all the CPU when no one else is using it. But let's say you think, oh, I need to make my application work for 1,000 concurrent users, or I need this latency, or I need this throughput, whatever. And as soon as we're moving to containers and we're kind of abstracting away from hosts, we have to understand that we're going to have multi-tenancy. And imagine we run our load test in one of our environments and nothing else was going on. We'd get all of the CPUs. Maybe this is a 32-core box. And then we would feel like heroes because we'd have maybe thought we were asking for one core. Maybe we'd set it to 1024 and we thought, yeah, that probably means one core. But actually, we get hundreds of thousands of TPS and we do fantastically well. We pat ourselves on the back. Then we go to production where utilization might be higher and suddenly our application performs completely differently. So if you don't like the idea of that, you actually want a fixed limit to how much total CPU you're going to want, then you want CPU quota, which is another cgroup feature. CPU quota works very differently. What it actually says is per a particular period of time, let's call it 100,000 microseconds, because that's the default for Docker. I would like this much time on the CPU. So we're looking at our Ratpack application here, and we're asking for 100,000 quota. What we're really saying here is, please, Mr. Operating System, can I have 100,000 microseconds of CPU time every 100,000 microseconds, and no more? And that's equivalent to one core, because it'll essentially say, okay, you've got this many microseconds, you better use a core for the entire period. If you want more than one core, you just go above the period. So if we've still got our period of 100,000, if we ask for 200,000 microseconds, and we don't have a TARDIS or some kind of time-traveling device or something, then the only way we can get more time on the CPU than the period is to be given multiple cores. Now, you might think, why is this important for me as an application developer? Well, once you've used your quota, and this was funny the first time I saw it happen, then the kernel takes you away. It throttles you. So imagine you've asked for a certain quota, your user requests come in, you've used all of your quota up, used all of those microseconds up, you are pulled off the CPU. And all of those outstanding requests will no longer get to complete. They will hang there. And then when you come to get back on the core, when the next period comes along, what's going to happen then is you're going to finish off those requests and you're going to get a large blip. You're going to get, say, X% of your requests took, 50 or 100 milliseconds longer because you were pulled off the core because of the scheduling done by cgroups. So it's really important to be aware of how this works. Control groups actually expose a metric to show how often that container, that control group is throttled. So rather than just blame it all on control groups, rather than blaming everything on garbage collection, which we do now, you can actually see a number and it says, has it actually been throttled in the last period? So if you're sick of looking at screenshots of terminals, then one of the first things I'd suggest you do if you don't already use it when you jump back to running your JVMs inside Docker is to get used to cAdvisor. cAdvisor is a tool from Google which itself can run inside a Docker container, which is always pretty weird from my perspective. And all it does is it reads that system, that file system, the sysfs, cgroup, and then presents us a nice pretty GUI. So we can instantly see for a particular container, and because we know that all of the containers, all of the cgroups live under Docker, it's aware of that. We can see the CPU shares. We can see which cores is it allowed on. We can see which memory limits. And more importantly, with cAdvisor, we can actually export those metrics to a central metric server like Prometheus or whatever metrics database you want. It exposes them over HTTP as well. So here we can get an aggregated view of all your JVMs running across your infrastructure inside Docker containers and see the stats, all these kind of the throttle stats, the CPU stats, the memory stats of that particular container. So if I put you to sleep for the last 50 minutes, I apologize. If you wake up now and think, what's just gone on, just remember two things. The first is you need to get an appropriate number of threads running inside your container. Otherwise, you're going to have to give it vastly more memory, and you're going to get killed a lot. You're going to get killed by the operating system. You know, we run most of our Java applications with double the amount of Docker memory or cgroup memory than the size of the heap. For actually getting that number, and they do differ depending on your application, I really don't have a better way to do it but to play with each application, hit it with some load, have a look at the native memory stats, and actually see how much memory it's using for each of the portions. So on that note, thank you very much for listening. I'm going to stick around here for any questions because I'm getting flashed at. So thank you very much.